6 feet below your home, the earth is holding a secret. While summer scorches the roof and winter freezes the windows, the soil beneath your foundation stays almost unchanged, hovering near 55 degrees Fahrenheit year-round in many parts of the United States. It is silent, stable, and always there like a hidden battery buried under every house. This is not a futuristic invention, it is an ancient one. More than 2,000 years ago, Persian engineers used underground cooling tunnels to preserve ice through brutal desert summers. The Romans adapted similar principles to bring cooler air into elite villas. And in modern Europe, especially in Germany, versions of this same idea are still being built today with simple materials and surprisingly low cost. So why do most Americans never hear about it? Why does a cooling method rooted in basic physics, proven across civilizations, and still functional in modern buildings seem almost invisible in the United States? In this video, we will uncover the forgotten science of the earth tube and thermal labyrinth, how the ground beneath your feet can cool a home, why this knowledge vanished from mainstream construction, and what it would take to build a version of it yourself today, using principles older than empires and simpler than the machines that replaced them in the last century. The reason this system works is simple but powerful. A few feet below the surface, the ground stops behaving like the weather. At that depth, the earth no longer responds quickly to hot afternoons, cold nights, heat waves, or winter storms. Instead, it holds a temperature close to the region's annual average, with only minor variation across the year. In practical terms, that means the soil beneath a home in Chicago may remain near 55 degrees Fahrenheit, while the air above swings from below zero in winter to over 90 in summer. In warmer regions, the underground temperature is higher, but still far more stable than outdoor air. The deeper you go, the less the seasons matter. This stability comes from thermal mass. Soil is dense, heavy, and slow to change temperature. It takes a large amount of energy to warm it up or cool it down, so surface heat moves downward only gradually. By the time summer warmth penetrates deeply into the ground, the season is already shifting. The same delay happens in reverse during winter. Engineers call this thermal lag, and it is why cellars, wine caves, and root storage rooms have stayed naturally cool for centuries without electricity. What matters is not that the ground is cold. What matters is that it is steady. A system that pulls air through the stable earth is not creating cooling out of nothing. It is borrowing the planet's own temperature balance, using the soil as a vast natural moderator between the chaos of the weather and the air inside a building. What makes this forgotten system so remarkable is not only that it works, but how efficiently it works. Modern air conditioners rely on compressors, refrigerants, coils, and high electrical demand to force heat out of a building. Even a decent residential unit typically delivers only a few units of cooling for every unit of electricity it consumes. An earth tube or thermal labyrinth works differently. Instead of manufacturing cold air, it passes incoming air through buried pipes surrounded by thermally stable soil. The ground absorbs excess heat in summer and softens extreme cold in winter. In many cases, the only electricity required is the small amount needed to run an inline fan that keeps air moving through the system. That difference changes everything. Rather than depending on a machine to fight the weather at full power, the system uses the earth itself as the primary thermal engine. The fan simply assists the process. The result is a form of cooling with dramatically lower energy demand, lower operating cost, and far less mechanical complexity than the equipment most homes are told to depend on today. Humanity did not discover this principle once. It discovered it again and again wherever people had to survive intense heat with limited resources. Long before modern HVAC systems, entire civilizations learned that the ground could store thermal stability better than the air above it. In ancient Persia, this knowledge reached extraordinary sophistication. Engineers built massive dome structures called yakhchals, or ice houses, designed to preserve ice through desert summers that pushed far above 100 degrees Fahrenheit. These structures were linked to underground tunnel systems, known as qanats, which carried water and cooled air across long distances beneath the earth. As hot desert air moved through those underground passages, it emerged dramatically cooler, allowing the Persians to create cold storage in one of the harshest climates on Earth. The Romans understood the same logic in a different architectural language. In elite villas, archaeologists have found evidence of air channels integrated beneath floors and through surrounding hillsides, allowing cooler subterranean air to circulate into living spaces. These were not crude improvisations. They were designed systems embedded into architecture as part of a larger understanding of comfort, airflow, and seasonal control. In Korea, underfloor channel systems evolved into thermal design traditions that regulated interior conditions through both hot and cold seasons. In the American Southwest, indigenous communities built semi-subterranean dwellings that use direct contact with the earth to soften temperature extremes long before industrial construction existed. These examples matter because they are independent. Persians, Romans, Koreans, and indigenous Americans were not copying a single blueprint from one shared source. They were responding to the same physical reality and reaching similar solutions across continents and centuries. That is the real story. Thermal labyrinths were not a strange historical accident. They were a repeated engineering answer to a universal problem. For thousands of years, people remembered what the Earth could do. Then, in the modern West, that memory was pushed aside by machines. The disappearance of this knowledge in the United States was not caused by physics failing. It was caused by a shift in culture, industry, and professional education. In the early 20th century, mechanical air conditioning began to transform from a specialized industrial solution into a symbol of modern life. Once that happened, older passive methods were no longer treated as valuable alternatives. They were treated as relics. The rise of mechanical cooling changed more than buildings. It changed expectations. Comfort became something delivered by a machine on demand at the push of a button. That idea was easy to market, easy to standardize, and highly profitable to scale. In that environment, Earth-based cooling systems looked old-fashioned, even if they remained effective. As building codes, engineering standards, and training programs evolved, the industry increasingly centered its assumptions around mechanical systems. Architects were taught to design with compressors and ducts in mind. Contractors were licensed around equipment they could install, replace, and service. Inspectors were trained to approve what codes already recognized. Over time, passive cooling strategies did not simply become less common. They became professionally invisible. That is why many builders today have never heard of the thermal labyrinths or earth tubes. Not because the idea was disproven, but because it was removed from the mainstream vocabulary of construction. A technology can vanish without being refuted. It only needs to be excluded from classroom standards and regulations long enough for an entire generation to forget it ever belonged there in the first place. While the United States largely forgot this approach, parts of Europe kept developing it. In Germany, Austria, and Switzerland, earth tube systems never fully disappeared from serious building design. Instead, they were studied, monitored, improved, and integrated into modern efficiency standards. In Germany, passive house research helped preserve interest in buried air systems as a way to reduce cooling demand without relying entirely on mechanical air conditioning. The logic was straightforward. If fresh air could be tempered by the ground before entering a building, then indoor comfort could be maintained with far less energy. Instead of asking a compressor to do all the work, the building itself could cooperate with the climate and the soil beneath it. Austria pushed the idea into larger institutional settings. Hospitals and other major buildings use earth contact air systems to reduce operating costs and stabilize indoor temperatures over long periods. That matters because large buildings are unforgiving test cases. If a passive strategy performs reliably, there it is far more difficult to dismiss as a niche experiment for hobbyists or idealists. Switzerland contributed something equally important: long-term engineering confidence. The question was never just whether these systems could work once, but whether they could continue working safely and efficiently for many years. European projects showed that with proper drainage, filtration, and maintenance, the systems remained durable, effective, and manageable over time. This is why the European example matters so much. It proves that earth tube cooling is not only an ancient curiosity or a romantic historical anecdote. It is a modern, documented, technically viable approach that continued evolving while other countries abandoned it. The knowledge was not lost everywhere. In some places, it simply kept maturing. If the physics is real and the international examples are strong, then the obvious question is this: why is the system still so rare in the United States? The answer is not a single ban or conspiracy. It is a layered problem made of codes, risk assumptions, and economic incentives. First, American building codes are generally written around familiar mechanical systems. Ductwork vents, insulation combustion safety, and HVAC performance standards all assume equipment that sits inside known regulatory categories. A buried air pathway does not fit neatly into that structure. When a system falls outside the template approval, it becomes more difficult, even if the underlying science is sound. Second, there are legitimate health concerns, especially around latent moisture and mold. In some regions, soil gases can create real risks if a poorly designed system draws contaminated air into a building. But this does not prove the concept is unworkable. It proves the design must be handled carefully with filtration, drainage testing, and site-specific judgment. Third, and most quietly, the dominant cooling economy rewards complexity. Conventional air conditioning supports a vast market of equipment, manufacturers, installers, maintenance contracts, refrigerants, and replacement cycles. A passive system that uses inexpensive buried pipe and a small fan threatens that model by reducing dependence on high-energy machinery. So the obstacle is not only technical, it is institutional. When a simple system cannot generate the same profit paperwork and recurring sales as a complex one, it often struggles to earn a place in the codebook. To build a simple version of this idea, you do not need exotic technology. You need a buried pathway, stable soil temperature, and careful control of airflow, moisture, and safety. In most cases, the system uses smooth HDPE or PVC pipe buried about 2 meters underground, deep enough to reach thermally stable earth and below the most dramatic surface fluctuations. The pipe run is often 30 to 60 meters long, giving incoming air enough time to exchange heat with the surrounding soil. In summer, hot outside, air enters the pipe and gives up heat to the cooler ground before reaching the building. In winter, bitter air arrives cold and leaves the pipe moderated. A small inline fan can help maintain steady airflow, but the earth is doing the real work. The details matter. The pipe should slope gently, so condensation drains away the intake, should sit away from contamination sources, and filtration should be added to control dust, insects, mold risk, and site-specific concerns such as radon. What this system offers is not magic. It offers a partnership with physics. Beneath every home, the planet is already holding a steady temperature waiting to be used. For thousands of years, civilizations understood that. Then modern construction forgot. But the ground did not forget. It is still there, still cool, and still waiting.